Okay, so for our calorimetry example, we're going to do an example of a calculation involving calorimetry. What we have here is a bunch of data, which are heat capacities for some materials. Some of them, for example, water as a liquid versus as a solid versus as a gas. The amount of energy that it takes to raise the temperature of liquid water is actually going to differ from that of solid water and gas, water in its gas phase, largely because of how those particles are interacting with each other. Now, we'll talk a lot more about this when we get into chapter 10. Suffice to say that it has to do with the intermolecular forces acting between those particles. We also have for some metals. You'll notice that the values for these metals tend to be much smaller values than what you have for water, and that's largely, again, because of intermolecular forces and intramolecular forces and what you get in metallic bonding. Turns out that metals are very good conductors of heat, which means it takes very little heat energy to raise the temperature per amount of metal. So let's get into our example problem. So this data we may be using here as we proceed through this example. So this example says, what will be the final temperature if a 10-gram piece of iron metal at 100 degrees is placed in 50 grams of water that's initially at 20 degrees Celsius? So what we have here, what we know is that based on the law of conservation of energy, the heat of the water will equal, or plus the heat of the iron will equal 0. And so we can use the idea of Q is equal to MC delta T to our advantage here. And so something we should be keeping in mind here is that iron metal will give energy to the water as heat. Okay. And so some things that are going to be useful for us, and here's the idea here. So Q for the water will equal negative Q for the metal. Okay. Now the temperature of the, so if we look at this from the standpoint of MC delta T, right, the mass of the water times the specific heat of the water times the delta T for the water will equal the mass of the iron times the specific heat of the iron times the change in temperature of the iron. And if I'm being really good about this, I'll remember my negative sign and put that out in front here. So let me rewrite my equal sign. There we go, the negative of that. Now, why is it a negative? Well, the water is gaining energy, right? So that delta T, remember delta T is equal to T final minus T initial. So if the final temperature of the water is higher than its initial temperature, that's going to be a positive value. And for the iron is going to a lower temperature, so it's going to have a negative value. So that negative sign there is to rectify the delta T's. Okay, so let's take now and actually look at one other thing here, is that the final temperature, that should be T final, not F final. So the final temperature for the water will be the same for both the iron and water. Because they're in contact with each other, they're going to come to the same temperature at the very end of this experiment, and that's the final temperature here. So let's put this together. Let's take and say our Q of the water is equal to negative Q of the iron, and start putting our pieces of data together. Now again, the data that I'm taking is from this question up in the top right, and should be a fairly simple setup for us. So we've got the mass of the iron is 10 grams, the mass of the water is 50 grams. Okay. The initial temperature of the water was, if we go back to this, 20 degrees Celsius. The initial temperature of the iron is 100 degrees Celsius. The initial temperature of the iron is equal to 100.0 degrees Celsius. Now, since we're dealing with temperature changes, it doesn't matter whether it's in Celsius or Kelvin, because temperature changes on those scale are going to be the same, right? Final temperature minus initial temperature, that difference will be the same. So it doesn't matter how we have it. So the other thing we need is the specific heat of the liquid water, okay? Which is, if we come back up here, 4.184 joules per gram degree. And the specific heat for the iron is, if we come back up here, so we had our water, we have our iron is here, 0.450 joules per gram degree. And we just plug in values, because remember, Q is equal to mc sub s delta T. So we can say our mass of the water times the specific heat of the water times delta T. I'm actually going to write this in here as an equation. So our delta T is going to be T final, and I'm not going to specify for the water here, because remember, T final for the water and iron are the same. That minus T initial for the water. Right? Final temperatures are going to be the same here. That will equal the mass of the negative, the mass of the iron, times the specific heat of the iron, times the final temperature minus the initial temperature of the iron. Okay, and so there's your equation that needs to be used. We really just have to plug in some values here for the masses, specific heats, and temperatures. So we have, for water, we had 50.0 grams times 4.184 joules per gram degree Celsius times T final minus 20.0 degrees Celsius is equal to negative 10.0 grams times the C sub S for iron, which is 0.450 joules per gram degree Celsius times T final minus T initial for the iron, which the initial temperature of the iron is 100 degrees Celsius. Okay. And so here what we can do is really just do some solving. So if we multiply some things out, we wind up getting 209.2. The grams cancel out, so joules per degree Celsius times TF, because I'm distributing that value to each of these, minus 4,184 joules okay, which should equal, joules should be times, make sure I've got my moment. and the degrees C will cancel out there because the degrees C, when it's multiplied by the specific heat, will cancel there. So that's why this is just in joules. And that'll equal negative 45.0 joules per degree C, because again, those are going to go away, times the final temperature, plus, because we've got to remember we're distributing the negative sign here. So we've got a negative there, and then the negative gets distributed there as well. Turn that into a positive, and we get 4,500 joules. Okay. And so here, we just get these on either side. We wind up with 254.2 joules per degree C times T, the final temperature, will equal 8,684 joules. We're just subtracting, right? Minus 4,184 joules. Just what I did there, so you can know that. So plus 45.0 joules per degree C times TF. So plus 45 joules per degree C times TF. And so then we just have to divide each side by the 254.2 joules per degree C. And our joules will cancel out. That all canceled out. The joules will cancel out. Degrees C will flip into the numerator. Our final temperature will be 34.2 degrees Celsius. And so something to keep in mind here, temperature, make sure, this is one of those places where you want to make sure your answer makes sense, right? If you were to get a negative temperature in here, that would be a problem because there's not going to be, there's not going to be a negative change, the final temperature, I guess it could be, if you do it in Kelvin, it's definitely not going to be negative. Here, in this case, though, you know that the temperature that's the final temperature should be higher than the initial temperature of the water and lower than the initial temperature of the metal. So that's something that you can keep track of there. Other questions could ask you to determine the specific heat of a substance. Specific heats are always positive values. You're never going to get a negative specific heat. So that's another thing to keep in mind as well. And so that really gives you a good solid example of how calorimetry can be used in a given experimental setting. Now in the next example, or the next section, we're going to start to look at how enthalpies of reactions that have been calculated through calorimetry can be used to figure out enthalpies of other chemical reactions that maybe you can't so easily and directly calculate. And that will be Hess's law.